Right, good to go. Look.
Yeah, I'll just wait that it's 15 sharp and then I'll go. Hey, good morning, everyone. Welcome back to the second to last exercise class, and it's also the last one with me. So next week will be Nuriya. What's the plan of today? We will have a short clarification of the lecture. In the Moodle, Lidia, so the other Lidia, uploaded a very well step-by-step explanation about it. I will just spend probably 5 minutes to explain some connections, which are probably easier if you explain it like speaking, except of writing. And the technical steps, these you can see in the lecture homepage. And if you have any question, then come back to us. Afterwards, we will focus on the trace and partial trace, which is topic of the exercise sheet, and we will look at properties and do maybe some exercises which are similar to what required, but not exactly, and also do some connection on what you're actually expected to do, why, and what's the physical meaning. And afterwards, we will comment on the double slit experiment, because I just realized that I remember that you solved this exercise, but actually you did it in the lecture a little bit less than what I thought. So we will just look at the Hamiltonian and comment on it, but this is also probably a 5-minute thing. One disclaimer, I have some pain in my right hand. I don't know where they come from. I'm very sorry, but I think I will write even less better than usual. I'm sorry. I'll just do my best that it's understandable, and please don't hesitate to write if something you can don't read. I can completely understand. So first of all, what's this? So the connection between the two and why it's important. So the ingredients here are the Hamiltonian for a central potential plus V of R, and here this operator is given by some constant, so minus EK square integral R. This is the operator of a central potential. And so this is the first ingredient you have, and the second ingredient is the Feynman-Helmand theorem, which you covered in the lecture. This is lecture 24. I'm not repeating exactly step by step, but just to say where we stand, what are we doing, and why. And the result, what is the result if we have 1 and 2? So these two ingredients, you calculated with the other Lidia that the expectation value of the 1/r operator is given by 1/n squared times a constant. Okay. Now, I just, while preparing for this and discussing, I looked at a book, and there was like this author, he was telling me, so if you don't appreciate the beauty of this theorem, you shouldn't study quantum mechanics. Because with one simple theorem, we can calculate the expectation value of the 1 over the position of our particle. And this reference of this book is also given in the comment about lecture 24. You can find in the homepage. So it's a way easier calculation than calculate the wall expectation value. Even sometimes it wouldn't be possible or very complicated. Here with the theorem, it's 4 steps of calculating a simple derivative and some expectation value, and you get this value. Now, what's the problem? So the problem is finding a connection between theory and experiment, which this is like the #1 question in physics. There is a kind of a fight between us theoreticians and experimentalists, because both of us think they are the best, and without us, physics would not exist. So why this? Because in theory we have this wonderful result. This, so 1/n square A is this expectation value. And this tells me that the expectation value of 1 over the position of the particle is approximately 1/n square A. And we had this particle rotating in a central potential. So we have kind of an estimation of the Bohr radius, estimation of 1/r, where RB, where RB is the Bohr radius. So we can give an expectation value of 1 over this length between the center of this and where this particle is rotating around. Now in an experiment, of course, you measure the expectation value of R, or better saying R, the distance, RB, so the Bohr radius, which we have a connection to the expectation value, the theoretical expectation value of the position operator. What is our problem? That in general, 1/r, so the expectation value of this, is not equal 1 over the expectation value of the position. And this is a central point in quantum mechanics in general. It can cause us many problems, but now we will see that under some assumption, we can use this and therefore calculate the expectation value of the position. So why is, why we have to look at the definition of the two operators. One is defined as psi integral over r, 1/r, and here psi, and the other is given as this. This is something I think you know by heart by now. R psi, so these are the two expectation values. This means that 1/r, like this, so 1 over the expectation value of the position operator will be 1 over like this. The R. So you can see that these and these have a different definition, and you cannot bring these parts here up, this and this. Now, why this? Why? So if you think about a number, if I have A and 1/a, it's given 1/a, to calculate A, I take 1/1/a, or like, or 1/a to the -1, and I can calculate A. The problem is in quantum mechanics is that if I have here R, so the expectation value of my position operator, I have a broadening, or this is something like this. We calculated these variance of an operator. The same will be for the expectation value of 1 over R. So if my 1 over R is here, I calculate this expectation value. This will have some broadening, okay? The particle has a probability of being in a region around, and the highest probability is at 1 over R, like exactly this value here. Therefore, so this makes, here is a bit the intuitive explanation why this in general is not valid. Now we can imagine so a special case, and this is satisfied in the case of the NLM eigenstates, which is the problem you saw in the lecture. Here we have that the variance of my operator is, let's say it goes to 0, but or it's very small, let's call it, or better, so variance of my operator divided by the expectation value of the operator. So this is the very mathematically corrected formula, is way smaller than 1, so it goes to 0. The two compared. This means that my the positions of the operator 1 over R, if the expectation value is here, this function, so the position R kind of peaks around here. As such, kind of a distribution similar to this. So it's very, very likely around 1 over R. So 1 over the position is very likely exactly the expectation value. And in this case, we can do the approximation that 1 over R, this expectation value is approximately 1 over R. Why this? Because it has very great probability that it's exactly at 1 over R, so that the 1 over the position is exactly 1 over R. If the distribution is more spread out, we cannot say it, or we could say it, but the approximation, we cannot write such a symbol because it's way too large, it's way too not precise. So here with this, we can say that the expectation value of the position of the particle is approximately n squared over R, and this is Bohr radius. And this you have connection, and this is with experimental measurement. Okay, do you have any question? So very important is that if you solve any other problem and you have such a situation, here, if you calculate such an operator, you don't say that the expectation value automatically is 1 over this. You can make some assumption, but you also have to motivate. Good. Then if this is clear, you can also come back later if anything is unclear. Otherwise, we move to point 2 of the exercise class, which is the trace. And a very short connection. I'm sure that you know the trace in linear algebra. So in linear algebra, if you have a matrix that is given of this form, then the trace of A is given as A plus E plus I. So its trace of A is the sum over I of the diagonal elements, or the trace is defined as the sum of the diagonal elements. In quantum mechanics, we have basically the same. It's just that we define it with, in the Cat-and-Brown notation, as we usually do with everything. And if we have a H is an operator of this type, where, let's write it as I did it. I know it's psi I, psi j, with psi orthonormal basis. Then the trace of this operator is defined as the sum over a j prime of psi j prime of all of the elements of my, so applied to my operator. And here I have psi j prime. And because of the orthonormal conditions of the basis element, this results as the sum over j prime of j prime, j prime. So here is because I applied these here to this to this, and this will give me a delta j prime I, and this to this, and this will give me a delta j prime. And therefore, I end up with this result. So here we kind of have, so the trace is the sum of the diagonal elements of an operator in its matrix representation. Here is exactly the definition, nothing new. I think you saw it in the lecture. What are the properties of this trace? First of all, it's linear. So the trace of some A I plus B is equal trace A plus B trace B. And yeah, a comment, if we work with operators, which we basically always do, it can be that we drop, and this you can also do in the exam, absolutely, that we don't write the head. Or if it's a matrix, usually then it's very clear that it's a matrix and has nothing to do with quantum mechanics, but most of the time we are anyway working with it. If you want to put heads everywhere because it's more clear for you, feel free to do it, absolutely good. And then the trace is cyclic, and this means that trace ABC is equal trace of BCA. And from these, so these are the properties that you have to show in the exercise sheet. But just a comment from this, it follows that the trace is a symmetric operation. So we have BA A. Okay, I think in this exercise sheet you only need this property, but this is also very useful in many other cases. And why this? Because if we define that D is equal BC, then we have from cyclic properties, we have that trace of AD is equal trace of DA, and then choose D equal B. Okay, we could call it maybe D B tilde, such it's very clear, D tilde, and then it follows, property follows. This probably you saw already in linear algebra. Again, here, these are both for operators or matrices. We can put ahead everywhere if we want, but as it's also valid for general matrices, we can also leave it away. And third property, the trace is basis independent. And this is very important if you think about it, because if we see here, we write an operator with respect to one basis, or we have to choose one orthonormal basis to define it. And we calculate the trace with respect to this orthonormal basis. But it turns out that actually the trace is basis independent. So no matter if here I choose another basis, psi I, psi j, here I will get, so gives same result. And I don't have to to worry about it. So this means that the trace of U A U dagger is equal the trace of A for U unitary operator. Great. If there are any questions, please raise your voice, write in the chat, because this was a bit, the introduction to move to the most important part of this exercise class, which I know you introduced it in last lecture, and you will still do it today. But it's so important because it's everywhere, quantum mechanics, in my opinion, it's very, very important that we do it. We stress it out a little bit more. And if you look at the home page of the lecture, it's written somewhere, if you want to only study one thing, because you don't have time, you don't care, then study the partial trace. Okay, such that you know this is not personal opinion, this is opinion also of your lecturer, which is properly more important. We move to the partial trace, which is 3.3 of our program. So what's the idea example? So if we have a qubit with probability 1/3 in state 0, and with probability 2/3 in state 1, we have that is characterized by the density operator rho equal 1/3 0 0 plus 2/3 1 1. And if this term is not that familiar to you, don't worry, because now we are going step by step. What does it mean and why do we construct such a thing? So the partial trace is also gives connection between probabilities and of states, quantum mechanics, and classical. So if we make a comparison, and we have classical and quantum, and we compare deterministic and probability distribution situations. So if we have a deterministic, we have, for example, a dice. This dice, we know that it has 6 possible states. So is 1 in general, 1 to D. So here, as an example, a dice returns 1 to till 6. Now in quantum, if we have kind of a deterministic, of course, white is bad. What if we have a deterministic configuration? Is a state as we knew up to now. So it's an element of the Hilbert space, which to be a valid state has to be normalized. And as an example, a qubit can be in the state psi is equal 1 over square root of 3 of the 0 state, and also of the 1, a superposition of the 1 and 0 state. And in 2 minutes, we will make a connection and what's the difference between this and this. Now, what's the probability of what's a probability configuration? Here we will have, so in this case, to make a beta connection is if I make a try, a dice will return one of the configuration between 1 and 6. But if I do 1,000 and I want to say, okay, what's my final configuration? I could define it as the number of times in which the dice returns 1, the 2, 3, 4, 5, and 6. So at the end, here I have a probability distribution. Therefore, I call it probabilistic. So I have probabilities for each of the configuration, and each of them must be greater or equal 0. And yeah, and as an example, for the dice, is probability it returns 1 to 6. So we have P1 is equal number of ones we get divided by the total number. I will correct it a bit afterwards in the note. Total tries and so on. So P2 is the times which the dice returns 2 divided by the time of the total tries. In quantum mechanics, if we have a state which is has a probability of being in one configuration and a probability on being another configuration, we call we characterize it with density operators, and we call this rho. So also here we can put a hat because it's an operator. What is the difference here? We will talk at it now. So a density operator, let's define it. So state psi I, so this is a normal state, has probability to, so to say, occur pi I. And this is, yeah, in the special case for discrete systems. So let's say like this, and then we define it. So we know that I have a configuration in which each state psi I has probability to occur pi I. So the question here is, what is the expectation value of a general A operator? So if we calculate it, we see A will be the sum over all of the states of the expectation value given by this state. Why? Because if I have a state psi, and I know that the system is in this state, the expectation value will be given by psi A, so bra psi A cat psi. This is exactly the expectation value of a state. Now I know that my total state, the system is in a configuration where different states are with certain probabilities. So I have to sum this expectation value and multiply it by this probability. For example, if I know that if I sell a book, I earn 20 francs. And if I sell a table, I earn 100. And I'm in a market. Now I have my total earning will be the probability that I sell the book times the earning, so 20 francs, plus the probability that I sell a table times the earning, so 100 francs. Okay, because if I sell way more books than table, then I have to take this into account for my total earning. And this is exactly what it comes out. Or for example, yeah, let's say that we say that for a dice, if the dice returns 2, you earn 40 francs, and if it returns 5, you earn 10 francs. So your total earning at the end will be the probability that the dice returns 2 times 20 francs plus the probability that the dice returns 5 times 30 francs. And this is your probability, your total earning at the end. So this is exactly the expectation value of my operator because of probability theory, not much more. Now, what can we see here? This is the definition. 1 to D. Yeah. What? Okay. Yeah. This is given by E equal 1 to D of Pi of the trace of psi I A, psi I, because of our definition of the trace. And then we use that the trace is cyclic. And this will give me then that I can rewrite it here as a trace of psi I A. So I revert to the order of this operator, which comes out here. Then I use that the trace is linear. And I can input this pre-coefficient here. Oh, sorry, I didn't want to write here. So I can write like this, of trace of A, sum over I, pi I, psi I, psi I. And therefore now I kind of divided what means the operator. So what's my operator, which is general operator, and it can be anything. Okay, of course, Hermitian, because we're in quantum mechanics. And what's the rest, which tells me informations about my state. And this is exactly what, so info about my state And this is the definition of the density operator. So this gives me the trace of the operator A. If I put here, I should put even here, A rho. And this is with rho is equal to the sum over some states. Each of them has a probability to occur, and like this. Okay. This is the density, the operator, the definition. Now, what is the difference? So the question is difference between psi is equal. So these two examples we saw before. And rho is equal 1/3 of 0, 0 plus 2/3, 1, 1. Okay. Sorry. So in one, we saw the probability of measurement in many, many weeks of the semester, but the key component is that the system is in state psi, and if we measure in the 0, 1 basis, we get 0 with, so we get the state 0 with probability 1/3 and 1 with probability 2/3. Okay, so the system is in a state, and we call it also a pure state, because the system is in a state. Now, what in the second case here is the system is in state 0 with probability 1/3 and is in state 1 with probability 2/3. Okay. The system has no defined state. Is in a in this case here in a superposition of basis state, but determined, and that's why if we looked here, I call it deterministic. Okay. If anything is unclear, please tell me, because I know that I had another quantum mechanics professor which sees quantum mechanics very differently, and then I started looking at this thing and I was like, oh wow, this makes so much sense. But it's maybe a bit tricky to see, because we define it and we discussed that here in this case the system is in a superposition, and you would say maybe here, okay, but this is also a superposition. But the fact is, here is a deterministic situation. Here, no, the system kind of fluctuates. We don't know, it has no defined state. Here we have a probability if we measure. Here we have a probability at any time. So the system has a probability for its own definition. And this will give us quite a lot of troubles. So yeah, now, yeah, as a comment, so for I, I can also write a density operator. So any state can be written as a density operator, but not every state can be written with the cat notation. Also, a mixed state as here, this we cannot write psi equals something, this doesn't work. But for I, rho is per definition the sum from 1 over d of psi I. And in this case, we know that the state has probability 1 of being in exactly this configuration. So this will give me P1 psi, or we can also write it psi1. So this is my psi1. So here I have to write P1, which this is equal 1, because the sum of probabilities of all of the probabilities of all of the configuration must be 1, of 1 over square root over 3 of 0 plus like this, 0 plus square root 2 over 3 of 1. And here the complex conjugate of this. So this will give 1 over square root of 3 bra 0 plus square root 2 over 3 bra 1. And these I can rewrite. Now I do a bit quick, but it's really like going from here, apply this to this to this, and so on. And this returns then plus square root 2 over 3 of 0, 1, like this, plus square root 2 over 3 of 1, 0, plus 2 over 3, 1, 1. Okay, and also here we can interpret this as each state with some probability. Okay. Is this difference clear? Okay, then it's great. We can still discuss about definition of maximally entangled states. And this is given by rho over, so this is the definition of my I over d of 1 over d. So each possible state which occurs of the Hilbert space has the same probability. So with psi I orthogonal to normal basis. Normal basis. So if each state of one of orthonormal basis occurs with the same probability, we have a maximally entangled state. Okay, and if you think about it, you have the least information possible in which state this system really is, because it has probability 1 over d of being in 1, 1 over b of being in 2, and so on. If one state has greater probability than the others to occur, then we have more information about the state. So in this case, the density matrix of this state is given, the density operator is given by the identity operator over d. So in matrix representation, we will have 1 over d. So all of the non-diagonal elements are 0, and the diagonal elements are 1 over d. Now, these density operators have some properties, which we will see now, and then we will have a break. So properties of density operators. First of all, the trace of any density operator must be 1. We will show them after the break. Then the density operator is Hermitian. Any density operator is Hermitian. And as a the last property is that we write it like this. So rho greater than 0, which means that it's positive semi-definite, which in case you still don't know what exactly is, no worries. It means that the expectation value of this density operator for any psi is greater or equal 0 for any psi element, for any element of the Hilbert space. Good. So after the break, we will show this property because it helps you learning a little bit how can you play with this density of operators, and then we will also cover a bit, make some connections with the exercises. So see you in 10 minutes. If you have any question, I will be online for the time. Welcome back. So in the break, I realized that actually these proofs don't use any new concept you've ever seen. So I wrote them down and you can look at them afterwards because there are more important things you have to do. And maybe just two comments. We use the definition of the trace, the definition of adjoint operators. Only thing is, the sum over all of the possibility of a probability distribution is 1. And second, sorry, I just got I got distracted. My bad. And second, yeah, the probability is greater than 0 for everything, and here as well, complex of a number square is always greater than 0. Okay, and yeah, if anything is unclear, come back and ask me any question. Great. So we have now the partial trace, which is something very nice. What's the idea? So we have two systems with two Hilbert spaces. Okay, and the total Hilbert space will be something like this. Okay, this we saw already many times. Now is if we have a state of the total Hilbert space H, and we only want to study the properties of H. Okay, so how? The question is, what can we do with it? Okay, this is actually one option, but the also other option is if H, so A and B, Alice and Bob as usual, A and B are far apart, is difficult to study the property, the global. So if I have a qubit here and another qubit is 100 kilometers away, I can study the property, and they are entangled among each other, okay, which is actually possible, maybe not 100 kilometers, but yeah. How can I study the properties of the global system? So in this case, I can apply some operation on my system. And then the other person, which is Bob 100 kilometers away, study the properties of the system far apart, and maybe we communicate, and this we will see it again later. Just to give an idea about I, so the first idea, and this is actually my research. Here I simplify it a bit too, yeah, but the idea is I have one qubit, and this is coupled to infinite many electrons because I want kind of control it. And so I have this particle and then many others. Let's call it, this is one qubit. Okay. And then I calculate, so the procedure is, first of all, I do some simplification. And I get a Hilbert space, which is discrete and finite. But this would, now it's absolutely not relevant at all. And then, second of all, I calculate the ground state. of H. And third, I want to study my qubit. So for example, I would say, okay, I have these infinite many electrons. What is if I eat them up? I calculate the ground state, but I have the ground state of the whole Hamiltonian. I don't care about everything because the infinite many electrons are simplified and everything else. So I want to forget about them. How can I do them? I like trace out the environment. Okay, and this is exactly the partial trace. I trace out what is not my qubit. So if I have here H is equal H qubit tensor product H electrons, I want to get rid of it, of this. Now we look at the definition of the operation we want to implement to get rid of it. And this is exactly the partial trace. So the definition is an operation. So if I trace out B, this operation brings me to the Hilbert space, the total Hilbert space, so H equal to only the Hilbert space of Alice, A. And it maps my density matrix on the whole system to the density matrix on A, equal, which is defined, and then we will look at what this operation exactly means. BP rho AP. So this is the density, and then here I apply again what's on the left side. What is B? So where B is an orthonormal basis of the Hilbert space of Bob. Okay, so I have a density matrix of A and B, and then I basically, to forget about my B, which I don't care, I sum over the basis spaces applied as a Bryan cat. So we kind of maybe calculate as a partial expectation value. And I don't change anything about A because A is what I'm interested on. Okay, so this is exactly the sum over the basis states, kind of a projection on the B Hilbert space, but it's not a projection operator as we knew before, because this just forgets about some entanglement feature. So here I just restrict it. And if in this density matrix, the elements which have the same B state on B, and we will see it later what exactly it means, we keep them and we forget about the rest. Anything isn't clear, let me know. Now we see some examples which makes probably easier to understand what exactly this operation means. Okay, so the first example is a pure state. And this reconducts also with what we saw some weeks ago about pure states. So if psi is a tensor product of two states, which I call psi 2b, And then I calculate, then so the question is, so the trace. So first of all, I have to calculate the density matrix. Okay. And in this case, as it's a pure state, is exactly defined as we saw before. So psi I, this will be, let's put one step and one additional step here. And this will be psi 1a, psi 2b, psi 1a, and the psi 2b. Okay. And yes, this then I can join what is in A and what in HA, what is in the Hilbert space A and what is in Hilbert space B, and I get something like this, which is absolutely equivalent with what we just saw. Okay. Now, what's the trace? Okay, so the trace, if I rewrite it as according to the definition before, this will be the sum of B, and I trace out B. Okay, this will be the sum over some basis states of 1A, B, B. Here, yeah, and then I apply psi I A, psi I A. So apply it to my density matrix. Here I have a tensor product which makes no sense and it's wrong. Psi 2b, okay, like this. And then I have to apply again the right side. So this kind of projection, which is tracing out my environment. So the state I'm not interested on. Now, how do I proceed? I apply what is in A to what's in A and what's in B. So I kind of divide the two, or because this makes everything easier, as we saw multiple cases which were different from now, but the procedure is the same. So I apply the identity operators in A to what regards A, and these basis states B to what's in B. Now, what do I have here? This will give me, of course, exactly the same, because identity operator don't change anything. And this is psi I. Yeah, I'm terrible at telling exactly, yeah, these states, you know what I mean. And then tensor product over B of the basis states applied to my state in B, psi 2, B, B, B. Okay. What is this? This is exactly trace of psi 2, psi 2. Why this? This is if we come back to the definition of the trace, which is very long ago, exactly here. Okay. Nothing else. We apply it to the operator. Now, what do we know? This is because of the property we just saw. One. The the trace of a density operator, and now I have to go back here, is normalized. Okay, this is property 1. So I have that here, what comes out is that psi IA, psi IA. So for a pure state, the reduced density matrix, so if I trace out the part of the Hilbert space I don't want to, I get exactly this. Okay, psi IA, psi IA, which is quite intuitive. If the two systems are kind of separated, we combine them and we re-separate them, we get exactly the two systems, or the two systems separated. Why am I telling about combining? This is like one separated system, a state in A, a state in B, and I make a combination with the partial trace, I re-separate them. And if I would apply the partial trace on A, of course, I mean, this is completely symmetric. Or if I want here, rho B will be the sum over A of basis states on A, and the identity matrix on B, and so on. Because A and B, you can switch between them. They are completely symmetric. Now, why are we calculating this? Well, if a state is not that well separated and combined, but it's actually A and B are mixed, so to say, then a separation makes a difference. We don't just get the state in A, because it also doesn't exist. So we now see a second example, which is a bit more interesting, and then you will probably understand why are they so important. If we have psi, which is equal a state we saw many times, it's also a Bell state. Now that you okay, and these we write for like simplified version. Also, these you saw already many times, so we put together so that we don't have to write a lot of tensor products and everything. The question is, what is the state in A? So how do I characterize, what would I see only in the Hilbert space A? First of all, I have to calculate the density matrix, okay, as usual. So these will be psi, and these are simple calculation. Will give 0, 0, 0, 0. I'm doing a little quick because this is something I assume you know it quite well, and it's not particularly interesting. So this is density matrix. What does the trace make? So the trace, so our basis of the Hilbert space B, in this case, is given by 0 and 1. Okay. So the tracing out B of rho AB means that we apply this formula here, which now I just copy because it's way more convenient. Like this, and I have to erase something. Here, it's given by this, is the sum over the basis states. So let's apply them. I will have here, okay, the identity matrix, and then the 0 state, and then rho AB. Same on the left side. 0 B, okay. And then this is one state. I have to sum over all basis states. 1B, rho B, and here also 1A, 1B. Okay. What does it give me here? So I don't write every step because first of all, you have to do it in exercise, and second of all, it's just a tedious calculation. I now show you how also after 2 or 3 times you do it, you can just make it faster. And what's the idea? So if you are here, so you apply this on this density matrix. So the density matrix is here. Now we see that we have a cat in B, which is 0, and a bra in B, which is 0. So if I take this element here, B, the cat and the bra are in 0, this means this will return 1. Or if I have 0B, 0B, and then I apply a 0B and a 0B, this will give 1 and 1. So this trace out my B, it cancels it, gives 1. And what is the state of A? 0 and 0. Okay. I will get therefore here a 1/2 of 0A, 0A. Now, if I apply the same here, so this, and this to this state, I say that now here my cat is in 0, but my bra is 1. So my bra in 1 applied to the cat 0 here will give a 0. So this, let's call it that we make here, this is a pink, my pink, and this is my violet. So for my pink, this stays, this will return 0, this will again return 0 because one of the B is in 1 and I have a 0 state. And here both of the B's in this term are 1, but here my B's are 0, so it will give me 0. Now about the second term, I trace out where the B is in 1. So here I will have 0. Here, in the second term, one of the B is 0, so it will return 0. Same here. Here, in the third term, both of the B's are in 1. This means it doesn't return 0. And both of the A's are in 1. So it means here I will have, yeah, great idea, writing white and white, 1A, 1A. Is this clear? Please tell me if you can, of course, also input this matrix here and do 1-by-1 calculation. Is exactly what I did. I just skipped one step and didn't rewrote everything on it. Probably do it once or twice, but you can see straight away, we know now that orthonormal operators are 0 if they are different and 1 if they are the same and they are applied in a bracket combination. So now I have the density matrix of my state, okay, of my state in A. So this is equal, oh my God, sorry, I'm really realizing that my hand is getting worse and worse and I'm writing worse and worse. This is the state of my system. So my system is with probability 1/2 in the state 0 and with probability 1/2 in the state 1. But it's not a deterministic state. Now we go to an example 3, which is rho A, B, So now I'm calling this in this way because it's exactly one of the exercise, and you have another example which I'm not covering it now. And this is given by so the density matrix is given in this form, and this is the density matrix of 0, 1, 0, 1 plus 1, 0, 1, 0 plus 1, 1. So now the configuration of the whole system is not in a state, but also in the whole system, in the whole Hilbert space, the system has probability 1/4 on being in the configuration 0, 0. It has probability 1/4 on being 0, 1, probability 1/4 in 1, 0, probability 1/4 in 1, 1. How does it look for HI? So how does it look for the system A, for Alice? We calculate again the trace of B. We trace out B of rho AB square. And this is again, so here it will give me again 1H0B rho AB in this way. And V plus 1 0 AB there, and then here 1A 1B. Okay, should bracket 0 1. This is very good. Yeah, thank you very much. This is, yeah. So these you understood, I guess, because of my explanation, and is absolutely correct. Thank you, Conrad. A case like this would also be a valid state, okay? But as I told, it's in probability 0, 1 with this, then it's exactly like this. Thank you very much. Now, if we calculate this, we get, and this is your exercise, 1/4 of 0, 0, 0, 0 plus 0, 0, 0, 0 plus 1, 1, 1, 1 plus 1, 1, 1, 1. And this we can also see it quite quickly. We have to keep only the states where the B's on the bra and cat are the same. So in this case, B's are the same. In this case, the B's are the same. In this case, the B's are the same, and also here. Okay, but so when we apply 0, we will keep this state and this state. When we apply the 1, so for this, we keep this state and this state. What does it return? This gives me exactly 1/2 of 0, 0. Sorry, 0. Oh, this is because here we traced out B. Sorry, so here 0. It's everything I told is correct. Is only I wrote B again, which makes no sense. Plus 1, 1, but explanation and everything was correct. So what do I get here? 0 plus 1, 1. Okay. What we see, this is equal rho A. So this we call it rho A ', or I don't know. So these two matrices, we started with different states on the global Hilbert space, and we got the same density operators for the part in A. Okay, and if you think about it, it also makes sense that it's possible, because if we have less information, it means that multiple configuration can give the same result. Okay, if we see that probabilities that it's good weather and you go in the mountains, if you look only the probability that you go in the mountains, it can also occur when it's bad weather, if you only look when you go in the mountains. So combination of multiple information makes a broader characterization, more possibilities. If you only look at one characteristic, it can be that more possibility give the same result. So the exercise 3 is how to differentiate. And we will talk also about it in 2 minutes. A small comment which is also exercise 2. If I get, oh, actually, no, it's actually exercise 3, and here is 4. Don't be afraid by the length of exercise sheet. Some exercises are really like exercise 1 in 2 lines of calculation, which are application of partial derivative is solved. So we split it in many small exercises. Some of them are quite straightforward. And so the partial trace satisfies normalization, its Hermitian, and semi-positive. And so if we have rho AB a density operator, it follows that rho A is also a density operator. Because these 3 properties were exactly the 3 properties we saw here. Why does it make sense? If you think about it, we never know how big our Hilbert space is, or because we can say, okay, we have this qubit, we look at this qubit, but this qubit is actually coupled to the environment, which is maybe the lab, and the lab is coupled to what outside comes. So any Hilbert space we look at, the density matrices, the density operators have to satisfy this requirement. And so this is the physical intuition. In any state we take, quantum mechanics has to work because it's always, or it could be always, coupled to a larger Hilbert space. Mathematically, you can prove it in ways which is very similar to what I did here, which is what I solved during the break and quickly discussed it. Now, the big question is, we have that 2 density operators are the same. And for symmetry, you can think about it. Now, we didn't calculate it. Also, the density operator in the Hilbert space B are in the 2 cases the same. If you see here, these 2 states, A and B, here and here, are completely symmetric. So A and B, the density operator in A and B must be exactly the same. How can we, but rho AP, so the density operators of the global system, are not the same. So we are characterizing 2 different systems. How can we understand if we are in rho AB or rho AB? This, okay, how can we understand which configuration we are? And option 1 is that you perform, actually in the exercise sheet is option 2. So let's call it 2, is perform operations on H total, so the whole Hilbert space, which is composed like this. And then you make just measurements. Okay, you can measure the probability of figuring out one state of the other, and you calculate it. And this is, for example, in the Bell basis. Now, what is the problem? If so, assume that Alice and Bob have the Hilbert space Hi and Hb. If Alice and Bob are far apart, so this was this example that we have 2 qubits, one is in Alice's lab, the other is in Bob's lab, and they are entangled. But how can you perform a global operation about it over kilometers? Usually it's not possible. Okay, so we cannot perform a global measurement. It's not possible. On the global basis, we cannot do it. Also, if you think about it, the 2 detectors, the 2 qubits are very far away. How can you apply a detector? So the option 2 would, 1 now, if we go accordingly to the exercise sheet, is local measurements and classical communication. And what's the idea here? What do we mean with classical communication? Is Alice performs a measurement, and communicate the result to Bob, and Bob performs a measurement. So in other words, is like if Alice measures 0, what measures Bob? And for this is you have this table which comes in the exercise sheet. I will now write it, and we try to understand what this means. It gives you the operator, so the density operator of the over the whole Hilbert space. And then it tells you it applies different measurements. And here XA, XB, and then Bell basis. So this is option 1. Option 2. Yeah, so this is exactly my option 2 here, which I should maybe write in another color, because just option 2. Okay, a global measurement. These are local ones. So Alice measures in 0 and 1, and Bob does the same. And here exactly in the X basis, so Alice measures in plus and minus states, which you should know by now, and Bob the same, minus states. Now this table gives 0, 0, or 1, 1. And now I fill the table and explain you what does it mean. And here is psi1, this 0, 0, or 1, 0, 1, or 1, 0, or 1, 1. And here I have plus, plus, or plus, minus, or minus, plus, or minus, minus. And here, sorry, my hand is getting worse and worse. Psi1, or psi2, or psi3, or psi4. Now, what does it mean? This means, so if I write this here, this means the probability of psi1 is greater than 0 for rho AB. This means that if I calculate this, the expectation value like this is greater than 0. And why don't I include the other states? This means that P of psi2 is equal 0, P of psi3 and P of psi4 are equal 0 for this state. Okay, this is the notation we use for this state. And in rho AB prime, and this is exactly what I was looking for rho AB prime, all of the 4 basis states have probability measurement greater than 0. What does it mean? If I perform a global measurement and I measure once psi3, this tells me, okay, I'm for sure in this state of the system. The system is in this configuration, not in this, because for this configuration, it's impossible to measure psi3. Now, as said, these configuration, these global measurements are very difficult to perform. So what do they say? Here is, this means if Alice measures 0 and Bob measures 0, so it's possible that Alice measures 0 and Bob measures 0. So here to write, so 0, 0 is a measurement means that the probability of 0, 0 is greater than 0. And the probability of 0, 0 is yeah, like this, or rho AB 0, 0. So this is Alice and this is Bob. So this is exactly, Alice makes measurements and say, okay, if I have, I measured 0, I measured 0, I measured 0, I measured 0, for example, if you see Alice, oh, let's put it 0, 1, 0, 1. Bob, in this case, 1, we see that for rho AB, they make their measurement. So Alice measures, Bob measures, and then they compare. And what do they see? Or mathematically, it comes out that if Alice is 0, Bob is 0, and the way around. And so if they perform a lot of measurements and they see this, it never occurs that they have a different configuration, then it turns out, okay, it's very likely that we are in this case. Why this? Because for rho AB prime prime, it can occur such a situation. It can be that the two have a different configuration, okay? And these you can mathematically calculate. So this means that P01 is greater than 0 and P10 is greater than 0, and the same for P00 greater than 0, P11 greater than 0. Okay. So if they only once measure that Alice has 1 and Bob has 0, they say, okay, we have this case. Okay. Now I took a bit longer than I expected. I will write, it's a very short comment about the double split experiment. This you can absolutely understand from my notes, I'm pretty sure. If then you have question, come back to me. Yeah, thank you very much. There was a typo correction. Here is a plus, a minus. Yeah, and then I wish you a good week and actually also have a nice holiday. We will organize some question session in January. So good luck with the exam preparation and don't hesitate to write any email or in the Moodle. And yeah, see you somewhere in the question session or in the exam. Thank you very much for your participation and yeah, wish you a nice day.